Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In my videos on the analysis and design of the common emitter and common collector configurations of the bipolar junction transistor, I demonstrated how the performance of these circuits was highly dependent on the DC current gain of the specific transistor placed in the circuit. In those videos, I claimed that I would show you how to make some simple changes to the circuit that will stabilize it to DC current gain variations. And that is what this video is all about. In this video, I will walk through the analysis and design of a beta-stabilized common emitter circuit. In the next video, I will select parts from my junk bin to put this on the bench and then reverse engineer this design based on the actual values that I'm able to find. Then I will go to the bench to see how successful I have been in stabilizing this circuit against variations in the DC current gain of randomly chosen transistors. In this analysis, I will be utilizing Kirchhoff's voltage law. Now, if you're not familiar with this, I have a video on that subject that you can take in to get a handle on it. There's a link to this video up in the corner for you. The second tool that I'm going to be utilizing is the Thevenin equivalent circuits. Now, this is a real weird one that is not at all intuitively obvious. But I have a video on this subject as well. If you're not familiar with this, there's a link to this video up in the corner for you. I have provided a go along with the video sheet, which contains the same step-by-step process for you, along with some additional equations for things like input impedance, output impedance, voltage gain, and the like. There is one mathematical sleight of hand that I will provide the derivation for in this sheet as well. You will find a link to this downloadable sheet in the description. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. I will begin with a very quick introduction to the starting place for our changes. We are starting with the common emitter circuit that I designed and analyzed in my video on basic BJT circuit analysis. With this, we had a single positive power supply, which we called VCC. We had a resistor between the collector and the power supply, which we called RC. And lastly, we had a resistor between the base and the power supply, which we called RB. The emitter was connected to ground and to the negative side of the power supply. Now, as I said before, the problem with the basic common emitter circuit is that its DC operating point was highly dependent on the DC current gain of the transistor. At that time, I told you that I would show you how to rein this in, making two changes to the basic circuit. The first change is with the addition of a resistor in the emitter circuit. We will call this RE. Now, if this emitter resistor is left without a bypass capacitor, it has two significant effects on the performance of the circuit. First, the input impedance increases, and that seems like a good thing. But second, the voltage gain decreases. Now, I will show this effect in the go along with the video sheet that I have provided. The second change is adding a resistor between the base and ground. We will call this resistor R2. Now, I'm also going to change what we call the resistor between the base and VCC from RB to R1. I'm doing this to bring it into compliance with what you will likely see elsewhere when addressing the topic. Now, these two changes seem innocent enough. But the reality is they significantly complicate the design and analysis process. However, if we apply certain rules of thumb to the problem, it becomes a much easier problem to solve. Now, I will unfold these rules of thumb as I proceed through the process of analysis. For the sake of this analysis and design, I'm going to assume a quiescent DC operating collector current of 1 milliamp. I will be using a 2N3904 transistor randomly chosen from my collection. We will need the DC current gain of the transistor. Now I'm going to choose a beta of 200. So what is the object of what we're going to be doing? Well, I'm going to calculate the value of the collector resistor RC. I'm going to calculate the value of the emitter resistor RE. And I'm going to calculate the values of the voltage divider resistors R1 and R2 using a 2N3904 NPN transistor with a DC current gain of 200 such that the collector current IC is 1 milliamp and the collector voltage VC relative to ground is in the middle of the available range. So let's begin this process. Well, I'm going to begin the design process at the emitter because this is where we get to apply our first rule of thumb. We start by recognizing what Ohm's law tells us about the value of the emitter resistor. It says that the value of the emitter resistor is equal to the voltage across the emitter resistor VRE divided by the current through it IRE. But at this point, we don't know either the voltage or the current associated with the emitter resistor. So how do we break this loose? We begin by establishing what the voltage will be on the emitter VE, which also sets the voltage across the emitter resistor VRE. But we don't have any information to base this on. This is where we get to leverage our first rule of thumb. This rule of thumb says that the emitter voltage will be the power supply voltage, VCC, divided by 10, or 2 volts, whichever happens to be less. So what do we know? We know that the power supply voltage, VCC, is 12 volts for our example here. This gives us that the emitter voltage is equal to 12 volts divided by 10, which gives us an emitter voltage of 1.2 volts. And well, 1.2 volts is less than 2 volts, so we will use 1.2 volts for the emitter voltage. Now the next thing that Ohm's law wants us to know is the current through the emitter resistor. We know that the emitter current is equal to the collector current times the quantity 1 plus beta divided by beta. So what do we know? We know that the collector current, IC, is 1 milliamp by our design constraints, and the DC current gain of the transistor, beta, is 200 by our design assumptions. Making these substitutions gives us an emitter current of 1 milliamp times 1 plus 200 divided by 200, which gives us an emitter current of 1.005 milliamps. Now we can return to our Ohm's law equation to solve for the value of the emitter resistor. Well, what do we know? We know that the voltage across the emitter resistor, VRE, is 1.2 volts by our rule of thumb, and the current through it, IRE, is 1.005 milliamps. Putting these known values into our equation, we get an emitter resistor value of 1.2 volts divided by 1.005 milliamps, which gives us an emitter resistor value of 1.194 k ohms. Now that we've determined the emitter resistor value, we can turn our attention to the collector. Well, we begin this process by going to Ohm's law to see what we need. According to Ohm's law, the value of the collector resistor is equal to the voltage across it divided by the current through it. But at this point, the only thing we know is the current through it by way of the design constraints. We're going to have to apply Kirchhoff's voltage law around the collector emitter loop to determine the voltage across the collector resistor. So I will start at the negative terminal of the power supply. As I travel from the negative side of the power supply to the positive side, this is an increase in voltage level. It is a positive voltage change. The next thing we come to in this loop is the collector resistor. As we travel through this resistor to the collector, we experience a voltage drop. This is a negative voltage change. Traveling from the collector to the emitter is yet another voltage drop, another negative voltage change. We have come to the emitter resistor and experience yet another voltage drop as we travel to the ground connection. This is a negative voltage change. We have finally arrived at the ground connection and back to the negative terminal of the power supply. Now, let's write the equation that describes this trip around the loop. We have the power supply, VCC, minus the voltage across the collector resistor, VRC, minus the voltage across the collector emitter of the transistor, VCE, minus the voltage across the emitter resistor, VRE, all equals 0. Now, remember, one of our design constraints is that the voltage across the collector emitter of the transistor will be half of the available voltage swing. But what exactly does this mean? Well, it means that if the voltage between the power supply and the emitter is 6 volts, then the voltage across the collector emitter will be 3 volts. But this also means that the voltage across the collector resistor will also be 3 volts. So, to satisfy this condition, we can say that the voltage between the collector and emitter of the transistor, VCE, is equal to the voltage across the collector resistor, VRC. So let's set both of these to the same variable. Let's say VQ. So our KVL equation becomes VCC minus VQ minus VQ minus VRE equals 0. Bringing the VQs together, we get VCC minus 2 times VQ minus VRE equals 0. So what do we know? We know that the power supply voltage VCC is 12 volts. We know that the voltage across the emitter resistor VRE is 1.2 volts per our previous calculation and via the rule of thumb. So putting these into our modified KVL equation, we get 12 volts minus 2 times VQ minus 1.2 volts equals 0. Well, now we get to rearrange things a little bit so that we get VQ on one side of the equal sign and everything else on the other side. So we get VQ is equal to 12 volts minus 1.2 volts on the numerator divided by 2. So the collector emitter voltage equals the collector resistor voltage equals 5.4 volts. So now we can return to our Ohm's law equation. And well, what do we know? We know that the voltage across the collector resistor, VRC, is 5.4 volts by our last calculation. We know that the current through it, IRC, is 1 milliamp by our design constraint. So making these substitutions gives us that the value of the collector resistor is equal to 5.4 volts divided by 1 milliamp, which yields a collector resistor value of 5.4 k ohms. Well, now we have successfully determined the values of both the emitter and the collector resistors. And so it's time to dive into the values of the voltage divider resistors R1 and R2. And this is where it gets just a little bit weird. While you could leverage Kirchhoff's current and voltage laws with another rule of thumb to find the values of R1 and R2, the most common way to accomplish this is through the use of a Thevenin equivalent for R1 and R2 with the power supply. Admittedly, the whole process is a little weird, but it works. The first step in creating our Thevenin equivalent is to disconnect R1 and R2 from the base of the transistor. So this becomes this. We now have a standalone circuit. Our question is, what is the open circuit voltage where the base would have been connected? This is the Thevenin equivalent voltage Thevenin. We have a simple voltage divider with a well-known equation of Thevenin is equal to VCC times R2, the output resistor, all divided by R1 plus R2. Now, we're going to set this aside for the moment. The next step is to turn all of the voltage sources into shorts and calculate the resulting resistance. This is the Thevenin equivalent resistance. The only voltage source here is the power supply, VCC. So by shorting this, R1 is now in parallel with R2. We use the commonly used equation for two resistors in parallel to calculate the Thevenin equivalent resistance. So R Thevenin is equal to R1 times R2 divided by R1 plus R2. It is with this Thevenin equivalent resistance that we get to apply our second rule of thumb, which states that R Thevenin is equal to the value of the emitter resistor times the quantity beta plus 1 divided by 10. So what do we know? Well, we know the value of the emitter resistor is 1.194 k ohms from our calculation. And we know that the DC current gain of our transistor, beta, is 200. Making these substitutions, we get R Thevenin is equal to 1,194 times 200 plus 1, all divided by 10, which gives us a Thevenin resistance of 24 k ohms. So, R Thevenin equals 24 k ohms equals R1 times R2 divided by R1 plus R2. Now we're going to set this one aside for a moment. We'll come back to this. What do we do with this new Thevenin and R Thevenin? Well, we get to refactor our schematic to include the Thevenin equivalent. And now it looks like this. Well, with this new schematic, our next step is to write the Kirchhoff's voltage equation around the Thevenin base emitter loop. Starting at the negative side of the Thevenin voltage and moving toward the positive side is a positive change in voltage. We then move through the Thevenin resistance for a negative change in voltage. Continuing on down through the base emitter junction, we have yet another negative change in voltage. And finally, we drop down through the emitter resistor for our final negative change in voltage, and we're back to the voltage source's negative terminal via the ground connection. Now, let's write the equation that describes this trip around the loop. We have the Thevenin voltage, Thevenin, minus the voltage across the Thevenin resistance, R Thevenin, minus the voltage across the base emitter junction, VBE, minus the voltage across the emitter resistor, VRE, is equal to 0. So, what do we know? Well, at this point, all we know is the voltage across the emitter resistor and the voltage across the base emitter junction. But that's all we know. So how do we get at the rest? Let's go at this one piece at a time. We start with Ohm's law and the Thevenin resistance. And it tells us that the voltage across the Thevenin resistance is equal to the current through it times the value of it. Well, the current through the Thevenin resistance is the same as the base current, and we know the base current is equal to the collector current divided by the DC current gain of the transistor beta. So what do we know? We know the collector current, IC, is equal to 1 milliamp per our design constraints. And we know the DC current gain, beta, is 200, well, by our assumptions. And this gives us a base current equal to 1 milliamp divided by 200. So our base current, and thus the current through the Thevenin resistance, is equal to 5 microamps. Now we get to go back to our Ohm's law equation. So what do we know? Now we know that the current through our Thevenin is 5 microamps by design constraint, and the value of our Thevenin is 24 k ohms per our rule of thumb. This gives us the voltage across our Thevenin is equal to 5 microamps times 24 k ohms, so the voltage drop across our Thevenin is 0.12 volts. Going back to our KVL equation, what do we know? Well, we know the voltage across our Thevenin, V our Thevenin, is 0.12 volts from our last calculation. The voltage across the base emitter junction, VBE, is 0.7 volts according to our model. The voltage across the emitter resistor, VRE, is 1.2 volts by our first rule of thumb, and this gives us V Thevenin minus 0.12 volts minus 0.7 volts minus 1.2 volts is equal to 0. Solving all of this for V Thevenin, we get V Thevenin is equal to 0.12 volts plus 0.7 volts plus 1.2 volts, which yields a Thevenin voltage of 2.02 volts. Now that we have everything set up with the Thevenin equivalent values, we can begin the process of calculating the values of R1 and R2. So where do we begin? We start by reminding ourselves of the Thevenin equations, which tell us that V Thevenin is equal to VCC times R2 divided by R1 plus R2, and R Thevenin is R1 times R2 divided by R1 plus R2. Doing a little mathematical magic, we can calculate the value of R1 with this equation. R1 is equal to R Thevenin times VCC divided by V Thevenin. And we know that R Thevenin is 24 k ohms by our rule of thumb. The power supply voltage, VCC, is 12 volts. And the Thevenin voltage, V Thevenin, is 2.02 volts from our previous calculation. So this gives us that R1 is equal to 24 k ohms times 12 volts, all divided by 2.02 volts, which yields a value of R1 of 142.57 k ohms. Well, now that we have R1, we drop back to the equation for R Thevenin so that we can calculate R2. We know that R Thevenin equals R1 times R2 over R1 plus R2, and we kind of rearrange this equation with a little mathematical manipulation to discover that R2 is equal to R Thevenin times R1 divided by R1 minus R Thevenin. At this point, we know that R Thevenin is 24 k ohms and R1 is 142.57 k ohms. So we get R2 equals 24 k ohms times 142.57 k ohms divided by 142.57 k ohms minus 24 k ohms, which gives us a value of R2 of 28.858 k ohms. Now that we've calculated the last value, what does the whole circuit look like? Well, here it is in all of its glory. And now that we have this, it's time to go to the junk box to see what parts we can find to put this on the bench. Well, part selection, reverse engineering, going to the bench to see its performance, and the bench results are the subjects of the next video. I'll also compare it against a comparable basic common emitter circuit. The results are simply amazing. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.